Hey, welcome back to Adventures in Engineering. Today is part 2 of my spindle installation upgrade on this Genmitsu ProverXL 4030. I am going to bench test, program, and install the spindle today. All right, here's my new VFD spindle. I have absolutely no affiliation to this company. I paid full price for it online, and I'm going to try it out, see how it is. Cable, wrench, some collets, the spindle itself. Some important things to note. Oh boy, this thing is heavy. Important things to note here. It's a 400 hertz spindle, 110 volt, 24,000 RPM. So that's going to matter when we go and program this thing. Let's see. Just some tools and some bits in there. There's the VFD controller. Let's see. Oh, that's interesting. I do not see a power cord, a 110 power cord. Okay, well, I might be able to find one around. Okay, I guess I'd say decent packaging. I'd say kind of a fail on not having a power cord for the controller. Well, I managed to find a power cord in my stash of stuff. Here's a wiring diagram for the wiring up to the motor and wiring up to the power source. So I'm going to go ahead and do those things and then just test to make sure the motor runs. Well, in a completely bonehead move, I cut off the wrong end of the cable, so the plug-in part, I guess I would have to have it plugged straight into the wall or something. I don't know. Anyway, managed to find another cord. So let's cut off the proper end, which is this one. Okay, moving on. Hello everyone and salutations! Today I'm going to explain an engineering concept using a whiteboard. I've decided to use the 48 volt output from the controller that's on the ProverXL and just run it straight into the controller for the VFD. Now, that presents a little bit of a problem because it outputs 0 to 48 volts, and the new spindle wants 0 to 10 volts into the controller. So a really basic solution, the simplest solution, is a voltage divider. So Vn equals 48 volts through R1 and R2. You get V out using this equation. The controller internal resistance replaces R2, which is approximately 10 kiloohms. So solving the equation, we end up with 38 k ohms. Well, after a little bit of testing, I determined that 33 k ohms yielded a little bit better result and always got me to full output, full 10 volt output. There were some losses in the signal. So that turned out to be the best result. So what I've done is run these wires into a 33K resistor that goes into the Vin on the controller, and then it's grounded, and the ground goes to the ground of the the control output to the old spindle. And what ends up happening is I get a full range drive of the new VFD. All VFDs have some level of programmability. I'm going to talk about this particular one, give you all the rundown. I'm going to save you a boatload of time with this cheat sheet. So, the VFD, it needs to be matched to the motor or the spindle, and the spindle has some information on it. You know, this one is a 400 hertz, 8 amp, 1.6 kilowatt or 1.5 kilowatt, 110 volts. So you need to set up your VFD to match those numbers. So we've got the frequencies need to be at 400, low frequency, high frequency, all this stuff. And then I changed the acceleration and deceleration time to be a little bit faster. These are the important ones for the motor, the speed or the frequency, and then 110 volts, 7 amps is the highest for this controller. 2 motor poles in this case. It was previously set to 4. And then the motor RPM, this was a strange one. I set it to 3,000 to end up getting 24,000 RPM out of it. Apparently it's 1/8 of whatever. I don't know why this is, but anyway, it came out to 24,000 when I set it to 3,000. I had to experiment a little bit to find that one. Then, when running with the controller with its own dial here, the PD070 was set to 1 for a 5 volt, and that's essentially for the knob control. And then I changed it to 0 for a 10 volt input from these wires. So that is how I got to the programming on the device. So now the way to test it is, since it's hooked up, and I can use the controller to turn on and off the spindle. So in this case, I need to unlock it, go to jog. Oh, come on, unlock. Okay, there we go. Go to the jog menu, and then, why is it not working? I forgot to put it on run. That's an important thing. Let's see. I'm going to turn this all the way down first. Change it to run. Okay. Now, and the dial on the side of the CNC controller allows me to turn up the speed to test the full capability. So now it says it's outputting 24,000. I put a little piece of reflective tape on the spindle. Come on. Give me something here. Well, it worked in rehearsal. Well, it turns out my RPM sensor, I replaced the battery, and I think it's working now. I had used it for approximately 30 seconds with the battery that came with it, and I guess that was too much for it. So I've replaced the battery, and now it seems to be working. So let's start this thing up. I've got it on a low RPM. It says it's running 1848. If I put this here, it says 1838. That's close enough, good enough for me. And I'm going to dial up the speed on the side of the CNC controller. And this says 13,400, 13,300 and something, so it seems we're, roughly 1% off. Now up to 24,000, 23,876. This is all acceptable for me. Bench test done. My next step is going to be to put some holes into this mount plate, or this XY plate, to hold this onto it like this. So we're going to put screws in from behind into these threaded nuts. And at first I was going to use a single centered hole like this, but what ends up happening is that sets up this right here, so it covers these holes that are pre-tapped and threaded for me, which is nice to have to mount the Z sensors like this. This is the way they were mounted before. I can either cut this one off and use the same stop switches, or make a new plate that will fit in that same space. So what I decided to do was change to an offset setup. So I'm going to move it this way. So I'll use these two holes this way. Then when I turn it over, I use the other two holes so that they line up. They'll line up here, and the whole thing will be slightly offset this way, which allows me access to these threaded holes over here. That slight offset that's created by moving it over this way is actually gained back by using the mount plate put onto this, and then the screws that go through the spindle into these threaded holes right here actually offset it slightly this way. So we're offsetting this way on the mount, and then we're offsetting this way to the spindle. It probably doesn't work out to be mathematically equal, but it won't be way off. All right, got my holes drilled, and I have some 10mm length, 5mm by 1, I think, threaded bolts to go into this. They are going to go into these right here, like so. I've already put the top two in place, and I'm going to get them into the top two on these. Okay, don't need to thread them in all the way because I need it to slide, and then I'm going to get in the other two next. Next, I'm going to try to get the Z-axis as close to vertical alignment as I possibly can by just sort of straightening this thing up a little bit. The L is fitting tightly up against both the top and the bottom, so at least it's perpendicular to the build plate. So the Z-axis slider is now on there firmly. Now I'm going to mount the adapter plate. These are 12mm long M5 screws. we go. Now it's time to mount the spindle. The thickness of the mount plate on the spindle is 11, and the thickness of this is, I think, 12.7, which is half an inch. And so I'm going to use a 20 millimeter long M6, and I chose M6 because of the size of the holes here. If I used an M5, there'd be a lot more play going through that hole. So let's mount this thing up. I think I'm going to move it down one set of screws because this distance here is almost, I think it's 46 millimeter, which won't get me to the bottom with some of my smaller 1/8 inch bits. So with something like this, where I'm going to be into it that far, I'm only going to have about an inch of bit sticking out, so I need to make sure that I can get to the bottom of the part when I'm cutting. So I'm going to change it up a little bit. All right, much better. That brings me down to about 20 millimeters of clearance here at the very bottom of the travel. And then that should allow me to use the entire 100 millimeter range of this Z-axis. Sweet. Okay, so if we come up, see how... So now the bottom of it is about level with the let's see. There, we're about level with the bottom of the Z-axis bottom plate here, and we've still got another 20 millimeters or so to go up. So that seems like a pretty good setup for the travel. It's also most stable probably in the middle of the spindle, mounting the spindle right in the center of it. So hey, I call it a win. Because I changed the orientation of where the spindle mounts, I need a new position for my air hose. So I am going to use the mount hole that it has. I'm going to drill into the mounting plate here and tap that so that I can mount it right there. Then it'll move with the spindle as it should. I'll probably tap both sides just so I can switch it back and forth. The way that I've set up my machine, my G-code will control the spindle properly. However, there's a catch. I have to set the parameters so that it will wait for the spindle to speed up. In my case, I've set it for 8 seconds ramp up and 8 seconds ramp down. So this parameter here, host processor default args, needs to be set to wait for spindle, and in the case of FreeCAD, it's using milliseconds. There are two different commands. One uses milliseconds, one uses seconds. So in this case, I set it for 8,000 equals 8 seconds. So that will delay once it turns on the spindle. It will delay for 8 seconds before it actually starts the program of moving and cutting. This is an example of the G-code output. The M3S12000 is setting the spindle speed to 12,000 RPM. The G4P8000 is delaying 8,000 milliseconds. If the P was an S, so it said G4S, then it would be seconds. So you need to check your CAM program and see which way it outputs it and set the number appropriately. One last configuration to be done is to set the CNC controller maximum speed for the spindle. The old spindle was a DC motor that had a 12,000 RPM maximum speed. The new is a VFD with a 24,000. So what we can do is pull up the parameters from the CNC machine with the $, and see here, number 30 equals 12,000 RPM. So we're going to change that to the new VFD value of number 30 equals 24000, 24,000. Enter, and we will clear the screen and then reload the parameters to verify. And you can see the new maximum spindle speed is 24,000. That will allow us to set in the CAM software to set the speed from 0 to 24,000 RPM and get the proper speed output out of the VFD. The VFD is showing that it's running in the forward direction. However, it's actually running in reverse. And so since it's a 3-phase system, you can just swap 2 of the 3 wires, excluding ground. So in this case, it's red, white, and black. You could swap red and white or white and black to get it to run in the opposite direction. And this is what I mean by that. So the cutting edge of the tool should be going this way, but it's actually spinning it that way, so it has to be switched. Now you can see it was spinning in the proper direction, the clockwise direction. Okay, so here's why swapping the wires works. A 3-phase motor has 3 windings, and a different sine wave phased by 120 degrees goes through it. So phase 1, phase 2, phase 3, and each of those sine waves causes the motor to spin a portion of its turn. So conceptually, you can think of it like a triangle. It goes 1, 2, 3, 1, 2, 3, 1, 2, 3. If you swap the wires, you swap 2 and 3, it goes 1, 2, 3, 1, 2, 3 in the opposite direction. And that's why we're able to switch the forward-reverse pattern by just swapping 2 wires. After reassembling my CNC machine, I went to test all the functionality and found that the Z-axis was moving in the opposite direction, and this is because I had turned it 180 degrees and changed the mounting point to the other side, so it just was moving the opposite direction. So to fix that, there is a step direction invert mask, which is number 3 in the Gerbil CNC parameters list. So to fix this, it's a bitwise mask, and if you don't know what a bitwise mask is, I'm going to teach you a bit right now. So a byte is 8 bits, and each 4 bits equals a nibble. So these are the lower ones, and these are the upper ones. So it's shifting from right to left. This is the least significant bit and the most significant bit. So in order to invert the z-axis, I needed to set its x here, y here, z here. So I set z equals 4. That is number 3 parameter equals the value of 4. That gives the z invert. If you wanted to invert x, you would set it to 1. If you wanted to invert y, you would set it to 2 because that is the value. So it goes 0 or 1. 2, 4, 8, 16, 32, 64, 128 are the value of each of those set bits. If you want to set more than one, like in the case you wanted to reverse x and y, you would set it like this. You would add the x value and the y value together. 1 and 2 equals 3, and that sets the lower 2 bits. If you wanted to set x and z, it would be 4 plus 1 equals 5, and then it would be 1, 0, 1. So that fixed my z-axis reverse problem.
I'm testing a dry run where I run it above the material just to make sure it looks like it's moving in the proper directions and depths and things before I actually cut the material. So far, looking good.
A mechanical engineering friend of mine suggested I use a 3-flute bit with a little bit less aggressive rise on the spirals. So here it is. I tried this bit, but unfortunately this one got all caked up with aluminum. Well, it turns out this bit has a coating on it which actually has aluminum in it. Well, aluminum on aluminum equals welding. So this bit did not do a very good job. It was, making these terrible edges because it was basically sticking to the metal as it went. So I've changed over to this non-coating bit. I'm going to try it, and I'm getting pretty aggressive here. I'm going to go with a 2 millimeter depth of cut. So let's see what happens. This should be a 0.1 millimeter depth of cut finish pass.
I didn't hear the motor bogging down or the spindle bogging down at all. It sounded like a very smooth cutting even at 2 millimeters. This is smooth to the touch. There is absolutely no ridging in there. And the edge may be a little bit sharp right here. There might be slight amount of burring on the top edge, but the inside edge you can see is nice and shiny. The bottom edge nice and shiny. I would say this was a definite win adding this spindle. It's Adventures in Engineering approved. I hope my videos help you with your projects. I'll keep posting. Consider subscribing. You never know, one day they might pay me like $5 for one of these videos.